We have already worked with how you can go about solving a linear equation. But now we're going to look at how to solve a system of equations. With a system of equations, what we're dealing with is more than one linear equation at a time. Let's say we had y equal 2x minus 3 and y equaling x plus 5. Now, since both of these equations are linear equations in two variables, a solution is going to be an x and a y value. It's not going to be an x and y value, though, that works in the first equation or works in the second. It's got to be an x and a y value that works in both of them. So one of the first things we need to be able to do is distinguish when we have a solution and when we don't. Let's say we were wondering, is the ordered pair 4, 5 a solution to this system of equations? Well, the only way to really find out is to try it and see. We'll take the first equation, substitute a 5 in for y, substitute in a 4 in for x, and what we end up with is an 8 minus 3. On our first attempt, we get a true statement. So we're seeing that it works in the first equation. But again, that's not absolute proof that it's a solution to the system. I now need to take the second equation and substitute. So basically, I've taken this equation, put in those values, and this time around, I get a false statement. So even though that ordered pair worked in the first, it did not work in the second equation. So that ordered pair is not a solution to the system. We could go and look at another point, still in an attempt to find a solution. Our next point that we're going to look at is going to be the ordered pair 8, 13. And we follow the same process. Taking the first equation and making the substitution for y and then x. This time, like last time, I get a true statement. So again, I see the first equation working. But that, again, is not enough. I have to take the second equation, plug in the y, plug in the x, and this time we see that it works both times. So I can conclude safely now that that ordered pair is a solution to this system of equations. Now, we have found one solution just by trying one that was offered to us. But what we need to know before we go looking for solutions on our own is how many we might find. With the typical linear equation, it is most common to find only one solution when you're dealing with a linear equation in one variable. When you get a linear equation in two variables, like either one of these, then you can freely pick x's, plug them in, and find the y's to go with them. So you can end up with, or you do end up with, an infinite number of solutions. But for a system like this, how many solutions might we have? Is there always going to be just one? Or could there be infinitely many? Or are there other possibilities? Well, since we are dealing with linear equations here, what we need to think about are the different things that can happen with two linear equations. Say this is our x and y axis. Let's look at some possibilities. Let's say that the two lines came down and struck each other at some point in the Cartesian plane. Well, this point where they have intersected one another, that point is an x and a y value, and it's an x and a y value that they share. In other words, it is an x value that gives the same y value for both equations for both lines. So anytime you have two lines intersecting like this, you're going to find yourself with one solution, which is exactly what we had in our example here with the 813. The reason that we had one solution like this is because the slopes were not the same. We can look back at these two original equations, and we found the first equation had a slope of 2. The second one had a slope of 1. Since those are not the same, that is the reason for the point of intersection. So you can simply get in the system of equations into the y equals mx plus b form, and if the slopes are at all different, you know you're going to have one solution. Now, the next possibility, one thing that lines can do is intersect. The other thing that two lines can do is simply be parallel. If you end up with two parallel lines, by definition, parallel means they're never going to intersect. So if you have no solution that is caused by parallel lines, then that is because the slopes were the same, but at the same time, notice that parallel lines hit the y-axis in different places. So we can say that the slopes were the same, but y-intercepts were different. That's caused parallel lines, and that implies no solution. Now, there's actually one more thing that can happen. You may think that either two lines intersect or they're parallel, and that's it. But there actually is one other thing that could possibly happen. Let's say that your two lines happen to have the exact same slope and the exact same y-intercept. That would mean that the two lines lay right on top of one another. Well, that's going to give you infinitely many solutions. Alright? Infinitely many solutions meaning any point that's on one line is automatically on both, since they fall one on top of the other. And this is caused by the equations, the entire equation, being exactly the same. So if you had, for example, a y equal 1/2 x plus 2 is for one of your equations, and y equal 1/2 x plus 2 for the other, then identical equations would give you coinciding lines, even though it's not always this readily obvious that they're identical equations. That can be easily found when you go to get the equation in your slope-intercept form. Now we have words to describe these three cases. Of course, each case implies a different number of solutions. One solution, none, infinitely many. But when you have only one solution like this because of the slopes being different, causing this intersection, this is referred to in most books as a consistent system. So if you see the phrase consistent system, that means one solution. When the two lines are parallel, that is called an inconsistent system. That means no solution. And when we have infinitely many solutions because of the overlapping lines, the coinciding lines, That is called a dependent system. So those are the three things that can happen. Now, we need to get into actually solving some of these equations. So let's take a look at how that can be done. Let's look at a few examples. All right. Our first example is going to be y equaling 3x minus 6 and y equaling negative x plus 6. Now we're going to learn first how to solve these things graphically. That will be our approach. There are other ways to solve, which we will also get into later on, but graphically is going to be the easiest probably because we're going to be able to use our graphics calculator. Of course, it's not the absolute best for every situation, but if your answer is a nice integer type answer, then the graphical approach will be just fine. All right, now I'm going to look at this first of all, and I can see in my first equation I have a slope of 3. In the second equation, I can see I have a slope of negative 1. Since the two slopes are different, I've got a consistent system, and I know I'm going to have only one solution. Now, some books might suggest that you go in here and try and graph this thing by hand and solve it. And that's really not the best way to do it. Not many people can draw that graph neatly enough to be able to come up with that solution. So let's go to the calculator. We're going to hit the y equal 2 button and type in our two equations. Type in the 3x minus 6, hit enter. Type in the negative x plus 6, hit enter. Now I'm going to do a zoom standard, and you see the two lines being drawn, and we clearly have a point of intersection here. The lines truly intersect in first quadrant, and we can hit the trace button, and hitting the trace will give us a little pointer where we can use that pointer to move along the graph to look for this point. So I'm going to use the right arrow to slowly move over in the direction of that point of intersection to try and gain a rough idea at least of what it is. And it looks to be, the calculator saying 2.9, 2.9. I'm wondering if the answer isn't 3, 3 because we're pretty close to that. Let's see if the calculator can do a better job of giving us a definite answer there. Alright, I'm going to go second, hit the trace button and get the calculate menu. Number 5 is intersect. And it asks you first curve, and up here we see 3x minus 6. Yes, that was it. So hit enter. Second curve, negative x plus 6. That was it. Hit enter. Guess. Now since we've already moved the cursor over here, we're already in position to make our guess. If the cursor wasn't here yet, you would need to move it. But when we hit enter, the calculator does tell us that the intersection occurs at 3, 3. And as a matter of fact, if you hit second and hit the graph button, you'll go to your table. And you can see for the x value of 3, we get matching y values of 3. So that absolutely definitely tells us that's where our solution is. Alright? So this one we easily solved with the help of the calculator. We found the solution was at 3, 3. Let's go to a new example. Alright, our next example is x plus 2y equaling 8 and 5x plus 2y equaling 0. Now that one isn't ready to be put in the calculator. I need to solve for y myself. So let's work with the first one. 2y equals and 8 minus x. I just subtracted x from both sides. Divide by 2. Y equal a 4 minus 1/2 x. And on the other one, I got a 2y equaling a negative 5x when I subtract it over. And I divide by 2, and I get a negative 5 halves x. So let's put those in. First one, go back to your y equal to, and clear what you had. And remember, our first equation was 4 minus 1/2 x. So we'll put that in. 4 minus 1/2 x. Hit enter. The other equation was negative 5 halves x. So we'll put that in. Negative 5 halves x. Now, we can look at this and once again see that our first slope and our second slope were not the same. Therefore, I can expect that I will have a point of intersection. When I look at the graph, I see that that is the case. So let's go through this process again. We will hit trace, this time going to the left to look for that point of intersection. It looks to be around negative 2, positive 5 perhaps. So let's see if that's correct. We'll go to the calculate menu, go to intersect, first curve, 4 minus 1/2 x, that was it. Hit enter. Second curve, negative 5 halves x, that was it. Hit enter. Guess. I've moved over, I've pointed at it, hit enter. It says the solution is negative 2, 5. Let's verify that with the table. Second function, graph button brings up the table. I'm going to go up 1, 2 to negative 2, and I get a matching 5 for the y values. That means that that was in fact your solution. So another easy example solved on the calculator. Now let's look at another example. Clear off the old. Our next example is x minus 2y equals 4 and 2x minus 4y equals 8. Again, solving for y. Subtract off the x. Divide off the negative 2. Get y equaling, let the negatives cancel, 1/2 x minus 2. On the other one, I have a 2x minus 4y equaling 8. Subtract off the 2x. Get a negative 4y equaling negative 2x plus 8. Divide by negative 4. Get y equaling a 1/2 x minus 2. Now look at what we have. We have the slopes being exactly the same, y-intercepts exactly the same. The two equations are in fact identical. So with this, you would simply say that you have infinitely many solutions because this is a dependent system. So that is pretty easy to spot once you solve for the y variable. So we don't even need to graph it. We know exactly what would happen. The two equations are the same, so the two graphs would be the same. And we really don't need to say any more about it than that. Now let's look at another example. Let's look at 2x plus y equaling negative 2 and 6x plus 3y equaling 6. Working with the first equation, subtract over the 2x. And I get a negative 2x minus 2. And the next equation, subtract over the 6x. Divide off the 3. Now here looks what we have. The first slope is negative 2. The other slope is negative 2. But the y-intercepts are different. Now we know what's going to happen, but we can look at it on the calculator. We have a negative 2x plus 2 for one equation. We have a negative 2x minus 2 for the other equation. When we graph that, we get parallel lines, and therefore we know that this system of equations has no solution. Didn't have to look at the graph to see that. We could have looked at the equation to find that out, but the graph just verifies what we already suspected was happening.